Because the whole point was he didn't know what she meant. Or thought she meant what she said. Alrighty, so we will continue on with our fun with one-dimensional Schrodinger equation. So I remember last time we were talking about the harmonic oscillator, and we were talking qualitatively about the idea of how the wave function changes character at the classical turning points. So just to review, I'll draw a more general looking kind of potential. Like let's say that that's what v of x looked like. Then let's say it just so happens that this energy works, that this gives a solution of the Schrodinger equation for that v of x. I don't know if it really does, I'm just sketching it in there. It gives us a solution of the Schrodinger equation that satisfies the boundary conditions. I have to be careful here. So remember that before I said that the mantra should be that it's the boundary conditions that put the quantum into quantum mechanics, and often students don't appreciate that. You can solve the Schrodinger equation in general for any arbitrary energy. You get a solution of the Schrodinger equation, but the problem is that it's not normalizable, that it doesn't go to zero as you go to plus and minus infinity, that it diverges. If you make it satisfy the boundary conditions at the classical turning points, for an arbitrary energy you can do that, but in general you find that such a solution diverges at either plus or minus infinity or both. So you can always get a solution, but it has to be a solution that is normalizable to count. That's why there's quantization of energy, because only at specific energies do you get the miraculous situation where you can satisfy the boundary conditions, including the ones at infinity, that the wave function has to trail off to zero as you go to plus or minus infinity. So what I'm really saying here is, let's just suppose this energy works as a solution which is normalizable, trails off to zero at plus or minus infinity, then these would be the two classical turning points. So a classical particle would bounce back and forth between those locations. Those would be where its energy had gone to zero. The force exerted on it had made it slow down, stop, and go back towards the origin again, and then go through and go back to here again, back and forth, back and forth. Classically, the particle would never be over here, because what would be true about it if it were over here? It would have negative kinetic energy. A classical particle doesn't like having negative kinetic energy. Really, quantum particles don't particularly like that either. But we said that the character of the wave function changes. So in between the classical turning points, the wave function is sinusoidal or trig-y. It's a wiggly thing. It's trig-y wiggly, right? Psi is trig-y wiggly in that region. Whereas outside there, we said psi was in our x-speed, freshly invented terminology. Psi is x-speed. So you got a trig-y region, you got an x-speed region, if you've got a bound state there. And things can get more entertaining. You could have a potential, say, that looked like this, let's just say. And then you can have different possibilities. Like, you could have a situation where the energy was up here, and in that case, there's only one turning point. In that case, that's our only turning point. And so it's trig-y over here, and x-speed over there. Or you could have a situation where, say, for that same potential, see how well I can duplicate my prior drawing, yeah, something like that. You could have an energy like this, This one's just going asymptotically to 0, but this one's doing something like that, let's say. Then there's two tricky regions and XD regions outside of that. And this would be a situation where I could imagine dropping the particle onto one side of the well, and if you solve the full time-dependent Schrodinger equation, you would find that it kept tunneling back and forth between the two sides of the well in that situation. And the higher the barrier, or the further apart they are, the longer would be the time interval between it tunneling back and forth between the two sides of the well. So there's all kinds of qualitatively fun behavior we can talk about. You could also have a situation where you have an energy eigenstate and it doesn't tunnel because it's got probabilities of being on either side of the well, and it's just in a stationary state. But those, well, enough of that for now. Anyway, then here's another situation. Suppose I had a potential that looks something like this. It's looking like a Gaussian. I'm not really necessarily implying that the wave function has a Gaussian shape. I'm sorry, that the potential, it's supposed to be the potential has a Gaussian shape. So let's say the energy's up there. So, for that energy, is that a bound state? Is it confined by the potential in any way? No, it isn't. To have a bound state, you have to have a region where the classical kinetic energy would be negative. It has to be where the potential energy is greater than the total energy in some regions. So this could represent a system classically where the particle comes in, say, from the left, and as it approaches the potential maximum, what would the particle do classically? Slow down, and then it would never stop. It would just keep on going and then speed up as it went away. It's symmetrical, though. It could come in from the other direction. Slow down, speed up again. Quantum mechanically, we could send in a wave packet. And quantum mechanically, you would find that there was some chance of reflection off of this thing. But in any case, quantum mechanically, this would represent a free particle here. It's essentially, it's a free particle because it never is bound by the potential. Are free particle energies, do you remember this, are free particle energies quantized or not? If the particle is not in a bound state, are the energies quantized? Turns out they're not in that condition. And that's because if the wave function is tricky, what does it do as you approach x equals plus infinity or minus infinity? Does it go to any kind of definite limit if the wave function is tricky? No, it just wiggles as you go to plus or minus infinity. And so, as a result of that, you don't have the problem of the wave function blowing up. It's not normalizable in the strict sense, however, because if it's oscillating, then the area under the curve doesn't do anything definite as you go to plus minus infinity. It keeps going up and down, up and down, up and down. But on the other hand, it generally won't diverge either. It's not blowing up. The area under the curve isn't infinite. It's just that, well, it depends on how far out you go, what the area under the curve is. And then as you keep going, area increases, but then it decreases, and then it increases, and then it decreases, and so forth. So, but on the other hand, well, that would be if it's really sinusoidal. Actually, excuse me. If the wave function were written as a complex exponential, far away, it would look like an e to the ikx or an e to the minus ikx type of situation, far away if the potential is going to 0. If you take psi star psi for that, that would be 1, right? And 1 is going to diverge. If you took the integral of psi star psi and it's e to the ikx in character or e to the minus ikx in character, that's going to diverge because if psi looks like e to the ikx, then psi squared would equal 1, and there's nothing you could multiply that by in order to keep the integral of psi star psi from diverging in that case. So the wave function isn't normalizable, but it turns out these are okay in a way that the ones that blow up are not. Because these can be normalized to the Dirac delta function, it turns out. And that doesn't mean anything to you yet, but it will. So let's start talking about the Dirac delta function. Do you guys do the Dirac delta function in PChem or not? No? Have you seen the Dirac delta function before? You would know if you had, so you probably haven't. But you guys have seen the Dirac delta function because we talked about it in 280 at the very least, and you might have seen it in other contexts as well. And what we're actually going to do here is solve for a delta function well. But first, let's talk about what a delta function is. So, the Dirac delta function, named after P.A.M. Dirac, who invented it because it would be useful and left it to the mathematicians to make it rigorous, to clean up after him, so to speak. Physicists are fond of doing that. The Dirac delta function is defined via, and I put it in quotes because there's no actual function that satisfies this definition, but we'll see that you can take a limit of a sequence of functions which comes closer and closer to satisfying this definition. Delta of x is equal to 0 if x is not equal to 0. So it's 0 everywhere except at x equals 0 where it's equal to infinity. So if I wanted to plot it, okay, 0, 0, 0, 0, 0, 0, infinity! 0, 0, 0, 0, 0. Well, it's hard to draw the point at infinity. It takes a long time to get there. So instead, we just represent it with a little spike at x equals 0, and that spike is saying, look at me, I'm going up to infinity. Actually, that says, look at me, I'm going up to infinity, and beyond, because it should really, be seeming bold and daring as it does so. Kind of like when we draw the infinite square well, we do two spikes to represent where it's going to infinity. But we need it to be a little bit more than that. It also, and part of the definition, is that the area under the curve is 1. Well, of course, what? The area under the curve is 1. The integral of delta of x dx is equal to 1. So it's 0 everywhere except at the origin where it's infinity, and the area under the graph is 1. And you rightly object to that. What? There's no function that can do that. What are you talking about? And that's why we really, and as we'll see, Dirac did that because it's very useful to have. It would be really nice if there were a function that did that. Later on, distribution theory was invented to make something that would do what Dirac wanted it to do. Delta of x can be viewed as the limit of an infinite sequence of functions. And it's not unique. There's lots of ways to define a sequence of functions that approaches these properties in the limit. Such as, let's define this function. I'm going to define a box function where it's equal to 0 everywhere except between minus a over 2 and a over 2. And in that range, it's equal to 1 over a. So we could define this box function. B sub a of x is equal to 1 over a minus a over 2 is less than x is less than a over 2, and 0 elsewhere. So look what happens with this thing. As a goes to 0, as you make it narrower and narrower, what happens to the height of the box? Bigger or smaller? It gets bigger and bigger, right? As a goes to 0, 1 over a, of course, goes to infinity. So the narrower the box, the taller it gets. And what's the area under the box? It's 1, right? Because it's a wide and 1 over a tall. So as you let a go to 0, you get something which has the property in that limit of having area under the curve be 1, 0 everywhere except at the origin where it's blown up to infinity. So no single one of these box functions satisfies the definition of the delta function. But as you let a get smaller and smaller, you get closer and closer to a function which does what you want. It's got unit area under the curve, and it's 0 everywhere except at 0 itself, x equals 0 itself, where it blows up. So really, an integral like this is really more something like limit as a goes to 0 of minus infinity to infinity of BA of x dx is equal to 1. Of course, it's 1 for the entire sequence, and so it's sort of automatically true. Well, it's automatically true here. But there's another property called the sifting property where this sort of idea will be more relevant. So really a delta function is to be thought of as the limit of a sequence, but then we just forget about that anyway, and we think of it as something that's 0 everywhere except at the origin where it's 1 and the area under the curve is 1. But there are other things that work as well. Can you think of another, I'll be impressed, can you think of another sequence of functions which is a little nicer behaved? It's got differentiability, right? This function isn't differentiable everywhere. It doesn't have a derivative at the edges of the box. Can you give me a differentiable function where there's a parameter you can control that will cause it to narrow up into an infinitely tall spike and have unit area under that spike? Let's see, if you were a genius mathematician whose name started with G, who would you be? You would be Gauss, right? Remember that we talked about the Gaussian function. The Gaussian function kind of looks like that, right? It's the normal distribution function. And for a Gaussian function, I'll call it f sub sigma of x, Gaussian function with standard deviation sigma, turns out to be that's 1 over sigma root 2 pi times e to the minus x squared over 2 sigma squared. That has standard deviation sigma. And the area under the curve is 1. That's the normalized Gaussian function with standard distribution sigma. And if I plug in sigma there, right, then I get sigma root 2 pi e to the minus sigma squared over 2 sigma squared, or in other words, 1 over sigma root 2 pi e to the minus 1/2 equals e to the minus 1/2 of its value at the origin, where it's a maximum. At the origin, e to the minus x squared over 2 sigma squared is 1. So at the origin, this thing's 1 over sigma root 2 pi. So at x equals sigma, then the Gaussian is down by a factor of e to the minus 1/2 compared to its value at the origin. So sigma represents a measure of the width of the Gaussian. Let's see, what's e to the minus 1/2? I don't know. So we got a calculator. I forget what e to the minus 1/2 is equal to. Nobody has a calculator here? Oh, okay. Wait, got my hopes up there. That was cool. You were genuinely trying to come through with it. Oh, does Steve have a calculator? Ah, our hero! Steve. E to the minus 1/2. 0.60653. No, because I'm going to sketch it on here, and I don't think I can go beyond about 0.6 for my 0.60 maybe. 60. What was the rest of it there? 653. 60653. Yeah, I can do a part of 10,000 there or 100,000 there. Times. So it's at 60% basically, or about 61% of its maximum value, right? Because the Gaussian is at a maximum at the origin. It's at the origin, right? This function peaks when x is equal to 0. So at x equals plus or minus sigma, it's down to about 61% of its value at the maximum. So if I go on here to where I'm down to about 61%, then that's 2 sigma between those 2 points, because it's plus or minus sigma either way. So if I did sigma over 2, then it'd be something else. But anyway, so sigma is a measure of the width of the Gaussian, which makes sense. It's supposed to be the standard deviation. Standard deviation measures the spread in a distribution. So sigma is a measure of the width of the Gaussian. And what value is this right here? What's the value of the peak? Yeah, 1 over sigma root 2 pi, because the exponential at x equals 0 is equal to 1, because it's e to the minus 0. And in my book, anything to the 0 is 1. So the height is 1 over sigma root 2 pi. The width is something like 2 sigma. What's the width when it goes to infinity on either, goes out to plus minus infinity on either side. But in that case, you define the width by some fraction that the function has fallen by. Often you would use the full width at half max, where you go down to 50% and say, what's that width? Well, that's expressible in terms of sigma, but here I'm just using 2 sigma as an effective measure of the width there. So, if I let sigma go to 0, then I have another sequence of functions which approaches the delta function, because as sigma goes to 0, the height goes to infinity. That's at the origin. And f sigma of x goes to 0 for any other x. Because as sigma gets smaller and smaller, then for any given x, eventually you're going to be at a point where sigma is a lot less than that x is, and so that'll be in the part of the curve which has gotten very narrow. So for some very small value of sigma, the Gaussian ends up looking something like, I can't even draw it very well, something like that. Drawn big, I didn't draw it quite right, but imagine a really narrow, tall Gaussian. And that's actually a preferable sequence to the box functions because it's differentiable, and that allows you to define the derivative of the delta function, for example. But for our purposes, this will be good enough. So the delta function has that property. Now, imagine that you're trying to describe the wave function of a particle which has a definite, well-defined position. Suppose I plot delta of x minus x naught. Where does that blow up? It blows up at x naught, right? It blows up at x equals x naught because when the origin is 0, when the argument is 0 is when the delta function blows up. So x minus x naught is 0 when x is equal to x naught. So delta of x minus x naught is 0 when x is equal to x naught. So that would plot like that. I would draw a delta spike at x equals x naught to represent that. So if I had a wave function whose absolute square was delta of x minus x naught, then you'd have a situation where what would be the probability of finding that particle at any value of x that isn't equal to x naught? It would be 0, right? It would be 0. And what about the probability of finding it at x naught itself? Yeah, it would be effectively 1. Now it kind of looks like, well, it would be infinite, right? But you have to remember that what you really do is say psi of x squared dx is the probability of finding it in dx. And so in this case, if I took psi of x squared dx, that would be delta of x minus x naught dx. And if I then integrate over a little region surrounding x naught, I'd be doing integral from, say, x naught minus a cute little epsilon to x naught plus a cute little epsilon of delta of x minus x naught dx. And that would give me 1, the area under delta of x minus x naught, same thing as the area under delta of x. That would give me 1 no matter how small epsilon is, because this function is 0 except right at x equals x naught. So, conclusion. Particle is guaranteed to be found at x equals x naught. So this wave function squared, if a particle's wave function squared was delta of x minus x naught, that would represent a situation where the particle has to be at x equals x naught and nowhere else. So the wave function itself would be the square root of the delta function, which would also be something which is 0 everywhere but infinite at the origin. And in fact, essentially, when you think about it, I guess the square root of the delta function is the delta function, I think. I think that's right. because that was, yeah, but anyway, the point is, yeah, so the point is that the delta function here at x minus x naught represents the wave function of a particle that has a definite position. Only it's not really a function, right? Because it you know, it's zero everywhere except infinite at some point. That's not really a function. But effectively, the delta function is the wave function of a particle that has a definite, well-defined position. Later on, we'll take that further and show that if you look at its Fourier transform to get the momentum space wave function, what you get is that the momentum space wave function has the same magnitude for all p. So, gee, if it's equally probable to find it for any momentum whatsoever, what do you know about the momentum in that case? You know nothing about the momentum. So if you know exactly where the particle is, you have no clue what its momentum is. And so that's you know, kind of the extreme of the uncertainty principle. If I knew exactly where it was, I'd know nothing about how the particle is moving. There's another property of the delta function that we need called the sifting property. Any questions? Consider the integral from minus infinity to infinity of some f of x delta of x minus x naught dx. Actually, I'll draw an axis there. So here's x. There's the delta spike at x equals x naught, and let's say this is our f of x, whatever it might be. So I'm going to multiply those two functions together and find out what the integral evaluates to. Let's look at our box functions and see what limit that would approach as our box functions get narrower and narrower. So let's draw a narrow little box function whose height again is 1 over a and whose width is a. So it goes from x naught minus a over 2 to x naught plus a over 2. Using our step function sequence, box function sequence, whatever you call it. This would be the limit as a approaches 0 of x naught minus a over 2 to x naught plus a over 2 of f of x times 1 over a dx, because the box functions are 0 outside the interval from x naught minus a over 2 to x naught plus a over 2, and it's 1 over a inside that interval. So the integral of f of x times 1 over a dx between x naught minus a over 2 and x naught plus a over 2 would be, in the limit that a goes to 0, what we would expect our original integral to be equal to. Does that make sense? Because that's an awfully good approximation as the box gets narrower and narrower. But for small a, we do the Riemann sum kind of thing. For small a, what inside that box? F of x is approximately equal to its value at x naught. If the box is really narrow, f is hardly changing at all within the width of the box. So it's a good approximation to say it's just approximately equal to its value in the middle of the box, namely f of x naught. Approximately just f of x naught in the region where the step function is non-zero. So we get approximately that I can just pull f of x naught out of the integral because it's a constant. The value of some particular x is a constant. F of x naught times the integral from x naught minus a over 2 to x naught plus a over 2 of 1 over a dx. And what's the value of that integral? 1 over a integrated over a box which goes from x naught minus a over 2 to x naught plus a over 2. What's that value of the integral? Yeah, it's 1, right? Because it's 1 over a tall, and along the x-axis it's a wide. We're back to the same situation where we're just finding the area under the box. 1 over a times a is the width that we're integrating over. So that's 1 again. Well, we shouldn't do that. So the integral is 1 over a times a equals 1. So in other words, for the integral, in the limit that a goes to 0, we just get f of x naught. And the conclusion, in other words, is that the integral from minus infinity to infinity of f of x delta of x minus x naught dx is f of x naught. In other words, the delta function picks out the value of f at x equals x naught. We say that the delta function clicks. That's actually the terminology we use. We say the delta function clicks at x equals x naught. So you imagine going along the x-axis, la 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 la. Suddenly it's x equals x naught, you go, and then you come back down to it. So it's clicking. And it picks out the value of f there. And this is what we call the sifting property of the delta function. You know, because if you like sift flour, you're working through it and all that. You know, it's like, let's find the bug in the flour. So you sift through all the flour until you find the bug, and you say, there it is. We don't do that latter part. But in any case, the delta function is doing the same thing. You know, it's sifting through all the values of f, and it's, this is the one I like. It's f of x naught. So that's the sifting property of the delta function. This moisture is making this chalk too soft. What is this reminiscent of? Why do we call this the delta function? Or else if you met something called a delta, the Kronecker delta, right? This is analogous to if I take the sum over n of Cn delta mn, the only one that lives is n equals m. Sum over n of Cn delta mn is Cm, because only when m is equal to n is that going to click, the Kronecker click, and then picks out that particular coefficient, the one where the arguments are equal of the delta Kronecker, the Kronecker delta. Here you're doing something similar. In other words, if you add up, that's what an integral is, if you add up a bunch of function values times delta function values, well, the only one that isn't zero is the one where the arguments are equal, where the x and the x naught are equal to one another, and that's the only thing that lives in your sum, f of x naught. So it's the same sort of thing. It might be even looks more direct if I said this in terms of what if I did a sum over n of f sub n delta, look at it like this, if it was a discrete sum over x of f sub x delta x comma x naught would be f sub x naught, if you were looking at discrete individual values of x instead of a continuous summation over x. So that's why it's the Dirac delta function, because it's analogous to the Kronecker delta, except that it's a continuous function instead of defined on discrete values, like the Kronecker delta is, where it's only defined on the integers. Now, we'll come back to this. We'll actually look at this as the wave function of a particle with a well-defined position. And we'll look at what its Fourier transform is and discover that it's e to the ikx times 1 over root 2 pi. Actually, it's e to the ikx minus x naught times 1 over root 2 pi. But that's for later. For now, the way we're going to use the delta function is to solve for the case of a well, a potential well, which is a delta function multiplied by minus alpha, as we shall see. But any questions before we move on here? Like, man, is this really this cool? And the answer to that would be yes. This is good stuff. If you disagree, you're wrong. Just checking to be sure that Alex is still with us. Yes, he is. So, consider the following. Now consider a potential well which is a delta function. So I want e of x is equal to minus alpha delta of x. Minus alpha delta of x. Well, that would be a limit of the following. The potential is everywhere 0, except at the origin where it's minus alpha times infinity, whatever the hell that means, right? But in other words, I can think of that as a limit of a box well, a finite square well, where the width of the well is A again. The width of the well is A. How deep do I want the well to be? This should be equal to minus what? Minus, not 1 over A, minus alpha times 1 over A. So what we're looking at is a finite square well in the limit that the the width of the finite square well, in the limit that the width of the well goes to 0 and the depth of the well goes to minus alpha infinity, so to speak. You know, again, really, it's of width A and of depth alpha over A. And then as A goes to 0, it gets deeper and deeper. And you can multiply a delta function by a number. 3 times the delta function has area under the curve of 3, and if I integrate it against any other function, it gives 3 times the value of the function where the delta function clicks. Did you have a question? Or you just no? Okay. All right. Okay. So later on, we're going to look at the finite square well and solve for that. And then this will be a limit of that in some appropriate sense. But it turns out, strangely enough, at first you might not think so, it turns out this is actually easier to solve by a long shot than the finite square well is, which is why we're doing this. This is actually easier to solve than a finite square well. Because, and you might be like, yeah, right, but it's because there's only one point where we need to match boundary conditions. With a finite square well, I got to match boundary conditions here and here, along with plus and minus infinity. That gives me more equations to worry about. But here, I only need this point and plus and minus infinity, the origin itself and plus and minus infinity, where I'm matching up my boundary conditions. I think that's best answered by just, we'll do it and you'll see what I mean as we do it. Yeah, rather than launch off on some general discussion, learn by doing, basically. Okay? So, our buddy Schreck gives us a commentary here. Schreck says, okay, what's the Schrodinger equation? We'll do the time-independent Schrodinger equation here. So the time-independent Schrodinger equation is, generically, it's something equals E psi. What's the something? What's that? Yeah, okay, I can't argue with you there. Okay, right? So H psi equals E psi. We'll even give it its hats. Okay, H psi is E psi. Not very helpful because, you know, again, there's no physics there until we say what H is. And it turns out in the real world, H can be written in the form. Yeah, right. Minus h bar squared over 2m d squared psi dx squared. In other words, the p squared operator operating on psi divided by 2m. Because p is minus I h bar d dx, so p squared is minus I squared, or it's equal to minus I times minus I, right, which is minus 1, times h bar squared times d dx on d dx, which is d squared dx squared, over 2m, right? So you know, think of this as literally being p operator squared over 2m plus potential energy operator, which is just v of x in the so-called x basis, plus v of x psi. Well, that was dignified. Yeah, by the way, Renee informed me today that she's not taking any more whining. So at least for now, don't go whining to Renee because you know you'll get one of these. So she'll set you on fire. So no complaining about it being 5th week and you got all these exams and all this kind of stuff.
I think she'll take it again.
You think so? You never know. I'm not going to say.
If she starts talking to you, then I think you can start talking. If she's grumpy, then
yeah, right. Yeah. If she's grumpy, you just like, hi Renee, how you doing? You know. So, all right. Minus h bar squared over 2m d squared, that's the generic time-independent Schrodinger equation. In this case, then, here what we're trying to solve is minus h bar squared over 2m d squared psi dx squared minus alpha delta of x psi of x is equal to e psi of x. This is our task, is to solve that equation. And we'll commence doing so after the break.